In this class, we discuss Gaussian wave packets. But before going into that, let's discuss Gaussian integration. We start with the gamma function, gamma of nu, which is a very useful tool when we try to solve certain integrals. Okay? So this gamma of nu is just the factorial function nu minus 1 factorial. And it's defined by this integral 0 to infinity e raised to minus x raised to nu minus 1 dx. Right? So if you are given an integral to solve, to evaluate, and if you can bring it to this form by certain substitutions, right, then evaluation of the integral is just finding the factorial. Right? For example, suppose you are able to bring a given integral to this form, e raised to minus y raised to 5 dy. All right. So we see that it's exactly in this form with nu minus 1 equal to 5. Right. So the answer has to be gamma of nu. So we see that nu minus 1 is 5. Nu is equal to 6. So we can simply write gamma of 6. So it's gamma of, yeah, it's gamma of 6. All right. That is 6 minus 1 factorial, which is 5 factorial. Right. So solving this integral just amounts to calculating a factorial. Okay. So this will turn out to be quite useful for us. Let's try to use the gamma function for Gaussian integration. All right. So functions of this form functions that go like e raised to minus x square, these are called as Gaussian functions. Gaussian functions. All right. So here we have got an integral of a Gaussian from minus infinity to infinity. All right. So we can use the gamma function to integrate this. Immediately we see that there is a problem because in the gamma functions the limits of integration are from 0 to infinity, whereas here the limits of integration are from minus infinity to infinity. All right. But this problem can be easily fixed. We see that this is an even function because we have got an x square here. So for an even function, integral minus infinity to infinity can be written as twice integral 0 to infinity. Right? So this integral, we write it like this. This is written as twice integral 0 to infinity e raised to minus ax square dx. All right. Now still, we have to do something more to bring it to this form. All right, because here we see that here we have got an e raised to minus x in the definition for gamma function. All right, so we need to write it in that form. Right, we can do that by making a simple substitution. We'll say that ax square is some y. All right, ax square will define a new variable called y. All right, to make the substitution, and then we can bring it to the form of a gamma function. Okay, let's see how we can do this. So the integral that we need to solve is I is equal to twice integral 0 to infinity e raised to minus ax square dx. Okay. Now we make the substitution y is equal to ax square. Right? If we take the square root on both sides, we see that square root of y is equal to square root of a multiplied by x. Now we take the derivative on both sides, we get half y raised to minus half dy is equal to square root of a multiplied by dx. Okay, so from here we can substitute for dx. Dx equal to 1 divided by 2 square root of a y raised to minus half dy. Alright, so if I make the substitution, all the substitutions in here, we have got a 2 here. This integral 0 to infinity. E raised to minus ax square is e raised to minus y. And dx is 1 by 2 square root of a y raised to minus half dy. Okay, this is a constant which can be pulled out of the integral, and this 2 will cancel with this 2. So this becomes I is equal to integral 0 to infinity e raised to minus y. There's a 1 by square root of a here. So, and we have got e raised to minus y raised to minus half dy. Right? Now we see that this now has the form of a gamma function. So we can compare it with the definition, the integral that defines the gamma function, and we see that they are exactly the same with nu minus 1 equal to minus half. Okay, here we have got a nu minus 1, and in that place we have got a minus half here. So nu is equal to 1 by 2. Okay, so the result of this integral is simply gamma of nu, which is gamma of 1 by 2. All right. And gamma of 1 by 2, if you refer back to your mathematical physics notes, you might have found that gamma of 1 by 2 is actually square root of pi. Right? So we can use this information and we can write I is equal to 1 by square root of a multiplied by square root of pi. Okay. So this is the integral that we got. I is equal to 1 by square root of a gamma of half. Now we use this result, gamma of half is equal to square root of pi, to finally obtain, this is the integral that we started with. Okay, integral minus infinity to infinity e raised to minus ax squared dx is equal to square root of pi by a. All right, this is a very important result. We'll be using it quite often. All right, many integrals that we want to solve can be brought to this form of a Gaussian integral, and then we know the solution. Okay, we just have to make some clever substitutions here and there. Now this result is correct even if the variable of integration is shifted in the complex plane by a constant. Alright, so what we have here is minus infinity to infinity e raised to minus ax square. Alright, now we could think of a variable that is shifted in the complex plane like this, x going to x plus some complex constant. Alright, then the integral would become minus infinity to infinity e raised to minus a x plus c whole square. All right. Now this, instead of this a, we could also have a complex number with the positive real part, right? With the real part of p being positive. Right. So that's the integral that we have here, minus infinity to infinity e raised to minus p t plus c whole square dt. So instead of x, I have used t here, and it has been shifted in the complex plane by a constant, right? By a constant c. And this p is also allowed to be complex, but in such a way that the real part of that is greater than 0. And in this condition also, we'll see that the same results hold. We can write this as square root of pi divided by p. All right. Now we haven't proved it here. The proof is quite simple. You can solve it using Cauchy's integral theorem. Okay, you can consider a loop like that, including the line and the shifted line. All right, and we know that the integral over a closed loop is 0. So you look for these things, and this will give the result that even if you shift, all right, this is the x-axis, this is the shifted axis, let's say in the complex plane. All right, and the integration from minus infinity to infinity does not change if you shift it in the complex plane by a constant. All right, so even if I have something like this, we can still use the result square root of pi by p. All right, so I leave it as an exercise for you to prove it if you have not yet done it. All right, so the easiest way to do this is to use the Cauchy's integral theorem. Right, integral theorem. So this Cauchy's integral theorem in this case can be written in such a way that the sum of a few integrals is equal to 0, and this actually would show that this minus infinity to infinity e raised to minus p t plus c whole square dt is also equal to square root of pi by p. Okay. So I include this result because we need this one also. We'll be using this one also. Right. So with that mathematical introduction, let's now look into Gaussian wave packets. All right. Now this is a physical example which illustrates our basic formalism, right? So we have looked at the position space wave functions, the momentum space wave functions. We know how to calculate expectation values in the position space wave function, etc. All right. So let's take an interesting type of wave function, which is called as a Gaussian wave packet, right? And then see how these things work in the case of a Gaussian wave packet. Okay. So we consider what is known as a Gaussian wave packet whose x-space wave function is given by this. All right, so this is the x-space wave function. We can write this as psi alpha of x prime, which is given by 1 by pi raised to 1 by 4 square root of d. This is the normalization part, and exponential I k x prime minus x prime square divided by 2d square. Now remember, without this term, right? Without this term, this is simply a plane wave. This is what we called as a plane wave, a momentum eigenfunction. All right, but here we have got something else. This, as we said, is a Gaussian function. All right, so multiplying the plane wave is a Gaussian function of the form e raised to minus x prime square divided by 2d square. All right, so what we have is a plane wave with a wave number k modulated by a Gaussian profile centered on the origin. Right, so if you look at this Gaussian function, we can show that, right? We can actually plot this Gaussian function. We'll see that it's a bell-shaped curve centered at the origin, Okay, all right. Now this is the Gaussian wave function that we are talking about. We could actually plot this, right? So in this plot, I have plotted both this exponential minus x prime square divided by 2d square part and the entire wave function. Right? So this exponential minus x prime square divided by 2d square part with this normalization factor gives this bell-shaped curve centered at 0, Right? So this is a bell-shaped curve. This is called a bell-shaped curve. Okay, and we see that this bell-shaped curve actually modulates the plane wave. It modulates the plane wave part here. Right? So if you had a simple plane wave, it would look something like that, the real part alone. All right, but if we have got a plane wave that is modulated by this Gaussian, so it looks like this. The plane wave goes like that. All right, we see that if you go from both sides from 0, all right, towards plus x part and negative x part, we see that these amplitudes decrease, where the amplitudes are actually decreasing. Okay, now in this the dotted lines correspond to the imaginary part. All right, the dotted lines here correspond to the imaginary part of e raised to ikx prime, or the entire function, right? The imaginary part of this entire function. So I have plotted both real and imaginary parts. Okay. Now the plotting is done for a fixed value of k equal to 1 and d equal to 10. Okay. Just as an example, we have plotted this wave function for k equal to 1 and d equal to 10. Okay. So as we said, we have got a Gaussian that is centered at the origin, which modulates this plane wave. Okay. So we have got a Gaussian envelope, so to speak. Now we know that the wave function is related to the probability of observing the particle. So by looking at the previous picture, we can already say that the probability of observing the particle vanishes very rapidly for mod x prime greater than d. All right. Now, if you really want to look at the probability density, this is given by the modulus square of the wave function. So let's plot the modulus square of the wave function. We see that the modulus square of the previous wave function, again with k equal to 1 and d equal to 10. Right? We are again talking about k equal to 1 and d equal to 10. All right, just as an example. So if I plot this modulus square of the Gaussian wave function, we get again a Gaussian shaped plot. Okay. This is called a Gaussian shape. It's a bell-shaped curve. Right? It's a bell-shaped curve. So here we see that the probability density has a Gaussian shape with width d. Okay, or we can say that the probability of observing the particle, right? So this is the case where x prime is equal to d. The probability of observing the particle is maximum at x prime equal to 0. It's maximum at x prime equal to 0. Right? And beyond x prime equal to d, which is 10 in this case, the, the, the height of this curve decreases rapidly, or the probability of finding the particle decreases rapidly. All right. So at the center, there's a maximum probability of observing the particle, which is represented by this sort of a Gaussian wave function. Okay. Let's now calculate the expectation values of x, x square, p and p square. The expectation value of x in the position basis is written as integral minus infinity to infinity dx prime. This is psi alpha star of x prime, and what we have here is psi alpha of x prime, because we know that bra x prime ket alpha is psi alpha of x prime. So bra alpha ket x prime is psi alpha star of x prime. We have already seen that this is how we calculate expectation values of operators in the position basis, or in the position representation, or in the coordinate representation. Now we know that bra alpha ket x prime is the complex conjugate of bra x prime ket alpha. So we can write this as integral minus infinity to infinity dx prime modulus square of bra x prime ket alpha x prime. Okay. Now the wave function we are talking about here is the Gaussian wave function. So you just substitute bra x prime ket alpha equal to the Gaussian wave function that we have already seen. And then you will see that this integral is 0. Because as you can check, the modulus squared of bra x prime ket alpha is an even function. Okay, x prime itself is an odd function. So the product of an even function and an odd function is again an odd function, which means that you are integrating an odd function from minus infinity to infinity, and that integral is going to be 0. You may convince yourself that this integral is actually 0 by substituting the Gaussian wave function in here. Okay, but you can also see that this integral, or this expectation value, has to be 0 from symmetry, because for example in the discrete case, we know that the expectation value can be written as, suppose position is discrete. Okay, in that case the expectation value can be written as sum over I p of xi multiplied by xi, which means you take each possible position, multiply it with the corresponding probability, and add all them up. That will give you the expectation value, okay, or the average value of x. right? Now what we have here is the continuum version of this, but the idea is the same, right? This integral is the continuum version of this expression. So that's why we have, instead of sum over I, we have an integral here, and in this case dx prime modulus square of bra x prime ket alpha. All right, this part is the probability for finding the particle between x prime and x prime plus dx, but it's the same idea. Now if we look at the probability plot, okay, you see that it's symmetric with respect to 0. It's symmetric about 0, right? So here we have plotted bra x prime mod ket alpha modulus squared. Right? This is called the probability amplitude, as we already have seen. But we see that, for example, if you take a position plus 10, right, the probability for that, right, the probability for position plus 10 is the same as the probability for position minus 10. Right? Similarly, the probability for any, let's say plus 1 is the same as the probability for minus 1. So when we carry out this summation or this integral, corresponding to every positive term, there's an equal and opposite, there's an equal negative term. Okay, so all this will cancel. All right, so because for example, let's consider this term. This is the probability for minus 10 multiplied by minus 10. All right, the contribution from this part, and the contribution from this part would be probability of plus 10 multiplied by plus 10. All right, and these two terms cancel, because the probability for minus 10 is the same as probability for plus 10, right? Because it's symmetric, because the probability plot, or in this case, the probability density plot is symmetric about 0, all right? So this probability for minus 10 and probability for plus 10 is equal. So this term will add up to 0. Likewise, corresponding to every term from here, every contribution from a minus number, there's a contribution, equal and opposite contribution from the plus part. Okay, which means that all these will add up to 0. So from the symmetry of this plot, or the symmetry of the Gaussian about 0, it's clear that the expectation value for x has to be equal to 0. Okay, I hope this is clear. Now let's calculate the expectation value for x squared. We know that in the state alpha, the expectation value for x squared is bra alpha x squared, operator x squared, get alpha. Okay, which in the position basis, as we have already seen, becomes integral minus infinity to infinity dx prime bra alpha ket x prime square bra x prime ket alpha. Okay, again, this is something that we have already seen when we discussed the coordinate representation. Now what we have here is the complex conjugate of this. So together we can write this as integral minus infinity to infinity dx prime x prime squared modulus square of bra x prime ket alpha. Now our bra x prime ket alpha, or the wave function, this is called psi alpha of x prime. This is the Gaussian wave function that we have already seen. Just substitute the Gaussian wave function in here. Okay, find the modulus squared, and then you can integrate it using the gamma function. All right, you will see that you can bring it to the form of the gamma function, and carrying out the integration, you see that the expectation value for x square is equal to d square divided by 2. The integration itself is quite straightforward, but still I shall guide you through the steps. So as we said, the expectation value for x square in the state alpha is bra alpha x squared get alpha, which in the position representation becomes integral minus infinity to infinity dx prime bra x prime get alpha star x prime squared bra x prime get alpha. Okay, I think you already know how to go from here to this expression. You just introduce the identity operator in here in terms of the completeness relation for the position eigengets. Right, you just use this I is equal to integral minus infinity to infinity dx prime get x prime bra x prime. This is something that we have done already, and then you can use the eigenvalue equation for the position eigengets and also the orthonormality relation, right? And then you will get the expression for the expectation value for x square in the coordinate representation. All right, now we can write this also as, because what we have here is the complex conjugate of this term, we can write this as integral minus infinity to infinity dx prime x prime squared modulus square of x prime bra x prime get alpha. Okay, here the wave function bra x prime ket alpha that we are talking about is the Gaussian. And the Gaussian wave function that we started with was 1 divided by pi raised to 1 by 4 square root of d exponential I k x prime minus x prime square divided by 2d square. Okay. When we find the modulus square, the pi raised to 1 by 4 squared gives square root of pi, and square root of d squared gives d. Okay. And here we have exponential I k x prime. But the modulus squared of exponential I k x prime is 1, because the modulus square would be exponential minus I k x prime multiplied by exponential I k x prime, which is equal to 1. Okay. Now the modulus square of the next term, exponential minus x prime square divided by 2d square. Right? The modulus square of this is simply the square of this term, because this is a real function. Alright. Now we know that e raised to a squared is equal to e raised to 2a. So the square of this is exponential twice minus x prime square divided by 2d square. Right? That's how we get this term. So bra x prime get alpha modulus squared is 1 divided by square root of pi d exponential minus x prime square divided by d square. Okay. To find the expectation value for x square, we just substitute bra x prime ket alpha modulus squared into this expression. Okay, and then integrate. You make the substitution and the integral becomes 1 divided by square root of pi d integral minus infinity to infinity d x prime squared exponential minus x prime squared divided by d square. Now we see that this integral is of an even function. This is an even function. Okay. Because if we substitute x prime by minus x prime, the value of the function does not change, because here we have x prime squared and here also we have x prime squared. Now the integral of this even function from minus infinity to plus infinity can be written as twice the integral of the same function from 0 to infinity. Now we can bring this integral to the form of the gamma function by making the substitution x prime square divided by d square is equal to y, or x prime square equal to y multiplied by d squared, or x prime is equal to y raised to half multiplied by d. Then dx prime becomes half y raised to minus half dy multiplied by d. Let's now substitute all this back into this integral. With these substitutions, the expectation value for x square can be written as 2 divided by square root of pi multiplied by d integral 0 to infinity. The term here half y raised to minus half dy multiplied by d, this was dx prime, and exponential minus y was exponential minus x prime square divided by d squared. Okay, and the y d square here is just, it was the x prime squared in the previous integral. Now we can simplify this. The 2 gets cancelled here. D here cancels with the d here. There's a d square left which can be pulled out of the integral, and inside the integral y raised to minus half multiplied by y here gives y raised to half. So the integral now becomes d square divided by root pi integral 0 to infinity y raised to half exponential minus y dy. Now we compare this with the expression for gamma function, the integral representation for gamma function. We know that gamma of z can be written as integral 0 to infinity exponential minus y raised to z minus 1 dy. Okay. Now comparing this, you see that in place of z minus 1 here we have got half. So z minus 1 is half, which means that z is equal to 3 by 2. So this integral is just gamma of 3 by 2. Then we have expectation value of x squared is equal to d squared divided by root pi gamma of 3 by 2. Now we can use the following property of gamma function. Gamma of z is equal to z minus 1 multiplied by gamma of z minus 1, which means that this expression can be written as d squared divided by root pi 1 by 2. Okay, z minus 1 is 1 by 2 here, multiplied by gamma of 1 by 2. And what's gamma of 1 by 2? This is something that you should remember. Gamma of 1 by 2 is equal to square root of pi. Okay. So we have expectation value of x square is equal to d square divided by root pi 1 by 2 multiplied by square root of pi, which is simply d squared divided by 2. So the expectation value of x squared calculated using the Gaussian wave function is d squared divided by 2. We found that the expectation value for x is equal to 0 and the expectation value for x squared is equal to d squared divided by 2. Now you can find the dispersion for the position operator. The dispersion is given by the expectation value of delta x squared, which can be calculated as the expectation value of x squared minus the square of the expectation value of x. But this term is 0 because in our case the expectation value for x is equal to 0. So the answer, the dispersion of the position operator is d square divided by 2. Okay. Using similar techniques, you can calculate the expectation value for the momentum operator, which can be written as expectation value for p is equal to integral minus infinity to infinity psi alpha star of x prime. Okay. And the expression, the representation of the momentum operator in the coordinate space, in the position space, okay, or the momentum operator in the coordinate representation is given as minus ih bar partial derivative with respect to x prime acting on psi alpha of x prime, and the integration is over x prime. Now for psi alpha of x prime here, you can use the Gaussian that we started with, okay, and you will have to find the derivative of the Gaussian wave function once with respect to x prime, multiply the resulting function with psi alpha star of x prime, which is the complex conjugate of the Gaussian. The integration is straightforward, and I shall leave it as an exercise for you to practice. Similarly, we can find the expectation value for p square, which is this integral, integral minus infinity to infinity, psi alpha star of x prime, all right? And in the coordinate space, or in the coordinate representation, the momentum operator twice, right? It is given by minus h bar square partial derivative with respect to x prime twice of psi alpha of x prime integrated over x prime. Again, you use the Gaussian wave function here, find the derivative twice. Okay, so once you can calculate the derivative once, and then you have to find the derivative of that function with respect to x prime once again. Okay, and then you will see that you will have to use the product rule to do the second what is the second partial derivative. So in this case, you will have to solve two integrals. Those integrals also I shall leave as leave as exercises for you, and if you do it correctly, you should get expectation value of p square is equal to h bar square divided by 2d square plus h bar square k square. Okay, this means that the momentum dispersion can be written as the expectation value of p square minus square of the expectation value of p. So you just do this and you get h bar square divided by 2d square. So this is the momentum dispersion. Now let's find the product of the dispersions. Now let's check the Heisenberg uncertainty relation. Okay, we have got the dispersion in the position operator, which is d square by 2, and the dispersion of the momentum operator is calculated as h bar square divided by 2d square. You just take the product, right, multiply these two, this d square will cancel off and you get h bar square divided by 4. Alright. Now if you remember the Heisenberg uncertainty relation, generally we write it as delta x square average delta p square average is greater than or equal to h bar square divided by 4. This h bar square divided by 4 was the minimum uncertainty. This was the minimum value for uncertainty. So we see that if I take a Gaussian wave packet, the uncertainty is minimum. Right? There is an uncertainty, but it has a minimum value. The product of the uncertainties actually, it is minimum. Alright, and here we see that it's independent of d. The width of the Gaussian does not appear here. Alright, so this is true for any Gaussian. This is true for Gaussian of any width. Alright, so we see that we have an equality relation rather than the more general inequality relation. For this reason, a Gaussian wave packet is often called a minimum uncertainty wave packet. If the state of the system is represented by a Gaussian wave packet, right, then it is a minimum uncertainty wave packet. Right? In that state, the product of the uncertainties of position and momentum takes the minimum possible value. It takes the least possible value. Now let's go to the momentum space wave function. Right? We already have the position space wave function psi alpha of x prime, which is given as the Gaussian wave packet. The Gaussian wave packet 1 divided by pi raised to 1 by 4. We had a square root of d, okay, and then exponential I k x prime minus x prime square divided by 2 d square. Right? This was our position space wave function. Right? Now we can find the momentum space wave function. We know that the position space wave function and the momentum space wave function are related by a Fourier transform. All right, so let me write it here. The momentum space wave function phi alpha of p prime can be written as, this was the Fourier transform. There was this factor 1 by 2 pi h bar and integral dx prime exponential minus I p prime x prime divided by h bar multiplied by psi alpha of x prime. So if you have the position space wave function, you just do this thing. Right? You just do the Fourier transform and you'll get the corresponding momentum space wave function. Right? So you have to take the position space wave function, multiply it by 1 by square root of 2 pi h bar e raised to I p prime x prime divided by h bar. Multiply it with this and then integrate over all space. Okay. So when I integrate over all space, the space part, all right, the space is integrated, it's gone, right? Then you will get a function of momentum. This function of momentum is called the momentum space wave function. And so you integrate over x prime, variable of integration is x prime, and then you will apply the limits for this integral, and then all x prime will vanish. You'll get a function of p prime. Okay, now this is what we need to do on the Gaussian wave function here in order to get the corresponding momentum space wave function. Right, so we have this factor 1 by square root of 2 pi h bar. There's an h bar there. All right, so it's 1 by square root of 2 pi h bar. And the wave function psi alpha of x prime has a normalization factor 1 by pi raised to 1 by 4 square root of d. That comes here, right? And then we write the integral minus infinity to infinity dx prime, right? And then exponential this thing multiplied by exponential minus I p prime x prime divided by h bar. All right. So when you multiply two exponentials, the arguments just get added up. Right? That's how we get this expression. Bra p prime ket alpha is equal to 1 by square root of 2 pi h bar, 1 by pi raised to 1 by 4 square root of d, integral minus infinity to infinity dx prime exponential minus I p prime x prime divided by h bar plus I k x prime, okay, the I k x prime from here, minus x prime square divided by 2d square. Okay, now we just need to integrate this. We just need to integrate this. All right, let's see how we can integrate this expression. Now this is what we need to do to find the momentum space wave function. Okay, so we are taking the Gaussian wave function that we started with and we are applying a Fourier transform to that. So we'll need to evaluate this integral. Right? So in order to evaluate this integral, we can use a trick called completing the square. So for example, let's look at the simple example. Suppose we have a term like minus infinity to infinity. We have an integral like minus infinity to infinity exponential minus x square plus 2ax. Right? Suppose we have an integral like this. All right. So here we notice that this x square plus 2ax are two terms in x plus a whole square. Right? Because if you look at x plus a whole square, this is x square plus 2ax plus a square. Okay, this means that x square plus 2ax can be written as x plus a whole square minus a square. Right? Now, if we make this substitution in here, this integral becomes integral minus infinity to infinity exponential minus, right? Here we have got x plus a whole square. Right? So we have got exponential x plus y can be written as exponential x multiplied by exponential y. Okay, so we can separate these terms and the other term is exponential minus a square. Okay, now this is a constant which can be pulled out of the integral, so this becomes e raised to minus a square, writing it in the shorthand notation. Right, and then we have got e raised minus infinity to infinity e raised to minus x plus a whole square dx. Okay, so I forgot a dx here, there should be the dx everywhere. All right, sorry. Okay. Now, in order to integrate this is quite simple because this has come to the familiar Gaussian integral form. Okay, this x plus a, right? You can make a substitution. We can call x plus a as simply y. Dx does not change. Dx is dy itself. The limits of the integral does not change. Right? So let me write it here. This can be written as e raised to minus a square integral minus infinity to infinity. Okay, e raised to minus y square dy. And we know this integral, we know that this is equal to square root of pi. Okay, so by completing the square, right, so what we have done here is that by completing the square, we have uh, brought it to the familiar Gaussian integral form. Right? That's exactly what we'll do here. Right? So let's take a close look at this integral. Right? I is equal to minus infinity to infinity dx prime exponential. Right? This is the integral that we have. Okay. So we see that there is this x prime square divided by 2d square in here. So let's just take minus 1 by 2d square outside. So we'll have an x prime square. Right? So we'll have an x prime square. So that's what I do. I take minus 1 by 2d square outside. This becomes x prime square. Okay. Now since I'm taking minus 1 by 2d square, I have to multiply it by minus 2d square to this term and to this term. Alright, that's why we have got minus 2d square. Alright, and these terms together can be written as ik minus ip prime by h bar multiplied by x prime. Okay, so I haven't done anything much. I have just taken this minus 1 by 2d square outside, and these terms, all right, these two terms are written as ik minus ip prime by h bar multiplied by x prime. Okay, so multiplying this with minus 2d square gives us this term. Okay, now we see that this is of the form x prime square, right, square of x prime plus something multiplied by x prime. So this is of the form that we talked about earlier. All right, only the difference is that there's an I appearing here, but that doesn't really matter. Okay, so we see that this is written as, this is of the form x prime square minus 2 x prime multiplied by a. Right, so if I take away this 2 x prime, whatever is left is the a. Okay, so this is of the form x prime square minus 2 x prime multiplied by a, where a is all this thing, d square ik minus ip prime divided by h bar. All right, now we can complete the square because this looks like two terms in the square of x prime minus a square. So let me write it carefully. So this minus 1 by 2d square is here. Right, now I am writing this as x prime minus, removing this 2 and x prime, right, x prime minus d square multiplied by ik minus ip prime divided by h bar. This is just the a that we had in the previous example, right, this whole square minus a square, because there is no a square term here, so minus the square of this term. Right, I hope this is clear. So the square of this term becomes d raised to 4, the square of this term, right, that is d raised to 4 ik minus ip prime divided by h bar whole square. Okay, now actually we have achieved what we wanted to do. This term is a constant, and we have got an exponential minus 1 by 2d square multiplied by this term. Right, this is a constant which can be pulled out of the integral. Okay, so let's do that. So this constant term is now pulled out of the integral, exponential minus 1 by 2d square and minus d raised to 4 ik minus ip prime divided by h bar whole square. Right, what we are left with is integral minus infinity to infinity dx prime exponential minus 1 by 2d square, and then x prime minus, let's say, sum a whole square. This is x prime minus sum a the whole square. Okay, now this can be simplified a little bit. I write this as exponential. This d square cancels with one of the d square in the numerator here, right? So we get like this, and the integral, this integral is the familiar Gaussian integral. Right, this is the familiar Gaussian integral, except that it's shifted in the complex plane by a complex number, by a complex constant. So there's a small shift in the complex plane, but we saw that, we did not prove, but we saw that we can use the same results. All right, this can be proved using the Cauchy integral theorem. All right, so this integral is something that we already know. This integral is square root of pi divided by a. All right, or a was the coefficient that appears here. So instead of a, we have got this minus 1 by 2d square. So this integral is simply square root of pi divided by 1 by 2d square. Square root of pi divided by 1 by 2d square. That's what I have here. See, this integral, this complicated looking integral, has been evaluated quite easily now. Right? So we just looked at it and we saw that we can complete the square and pull out a constant term. Right? So we still have this term here. So we write it like this: exponential minus d square by 2. Okay. So if I take the LCM, I can write this as h bar k minus p divided by h bar whole square. So I just rearrange this. This becomes square root of 2 pi. There's a 1 by 2 here, right? So you just have to multiply by the, what do you say, the reciprocal of this denominator, right? So this is 2d square divided by 1. Okay, so this is square root of 2 pi, and square root of d square is simply d. Okay. Now this is only the integral part. We also had this constant multiplying I. So if I multiply this constant to this I that we found here, we finally get the momentum space wave function. Right? You can do the multiplication. You see that there are some cancellations, etc., and we get square root of d divided by h bar square root of pi. All this inside the square root. Okay, and then exponential minus d square by 2 p minus h bar k whole divided by h bar whole square. Okay, so here I have written this as h bar k minus p the whole square. Okay, but h bar k minus p the whole square is also p minus h bar k the whole square. Right? So we can write this as p minus h bar k whole square divided by h bar square. All right, so the only thing that we have done from going from this step to this step is we have simply used a minus b whole square is simply equal to b minus a whole square. Okay. So we are done. We have found the momentum space wave function by completing the square and using the Gaussian integral. Okay. So we got the momentum space wave function by Fourier transforming the position space wave function. All right. Now we could use this wave function to find the expectation value of p and expectation value of p square. Right. This would be easier. This would be easier with the momentum space wave function because the action of momentum operator in the momentum space wave function is simpler. Okay, because of the eigenvalue equations that you can use, right? So you can try to find expectation value of expectation value of p and expectation value of p square in this wave function, right? Try to find it in this wave function. And this is also left as an exercise. Okay. Now the probability of finding the particle with momentum p prime. So if you look at this wave function, we see that it's a Gaussian. If I take the modulus square of this, it's a Gaussian that is centered at h bar k. It's centered at h bar k. In the case of the position space wave function, it was centered at x equal to 0. Right? The Gaussian was centered at x equal to 0. This is shifted by h bar k from p prime equal to 0. Okay. So the probability of finding the particle with momentum p prime is a Gaussian in momentum space centered on h bar k. Just as the probability of finding the particle at x prime is Gaussian in position space centered on 0. Right? So we see that it's still a Gaussian. Right? When I Fourier transform a Gaussian, I still get a Gaussian. All right. So we had a Gaussian wave function in the position space. Now we have a Gaussian wave function in the momentum space. All right. So we could actually plot the probability for finding each value of momentum. So we could plot p versus this modulus square of this wave function, and you get a Gaussian which is centered at h bar k, Okay. Now, furthermore, the widths of the two Gaussians are inversely proportional to each other. Right. So we see that earlier we had this d square in the denominator. In the position space, we had the d square in the denominator. Now this d square is in the numerator. So we could write this d square in the denominator as 1 by d square. Right. So this term characterizes the width. Whatever appears in the denominator here characterizes the width. All right, width of the Gaussian. So we see that the widths of the two Gaussians are inversely proportional to each other, which is just another way of expressing the constancy of the uncertainty product explicitly computed. Right. So this uncertainty product we saw is a constant. It was h bar square divided by 4. Which means that when the position becomes more and more accurate, the momentum becomes more and more uncertain. Well, this is what we are seeing here. Right? So suppose we bring down the width of the position space wave function. Suppose we bring down the width of the position space wave function. All right. So it will become peaked like that. Okay. So if d is very small, the width of the momentum space wave function goes like 1 by d square. So if d is very small, then 1 by d square is very big. 1 by d square is very big, right? So if the position space wave function is like this, the momentum space wave function will be spread out. The momentum space wave function will be extremely spread out. It will be actually the momentum space probability amplitudes will be extremely spread out. Okay. So this is another way of looking at the uncertainty principle, right? If the momentum space wave function is peaked at a point which corresponds to a certain position, right? We are sure that the particle will be found in a very small interval. Right? This means that we have a fair amount of certainty regarding the position of the particle, right? Then you will see that the wave function or the probability amplitudes for the momentum, uh, for measuring a particular value of momentum, right, or for measuring different values of momentum, it becomes more and more spread out. Okay. Now this means that the wider the spread in the p space, the narrower the spread in the x space, and vice versa. Right. Now, as an extreme example, suppose we let d tends to infinity. Right. So if you remember our Gaussian wave function, we had two terms in it. We had exponential ikx minus something like x prime square divided by 2d square, I think. Right. So when d tends to infinity, this term just goes to 0. Right. And we simply get a plane wave. All right. This is the real part of the plane wave e raised to ikx. Okay. Now the position space wave function then becomes a plane wave extending over all space. It is extending over all space, right? It's extending over all space. The probability of finding the particle is just a constant independent of x prime, right? So if we take d tends to infinity, we see that the probability of finding the particle is just a constant because we'll get plane wave which is spread out through the entire space, right, which is spread out over the entire space, right. Now I am drawing only the real part here. We could also draw the imaginary part, right. So if I take the imaginary part, we'll see that, and if you calculate the probability amplitude by the usual postulate, you will see that you have a constant probability at every point, right? For example, if I take modulus square of e raised to ikx, because this is the plane wave, right, this is 1. This is simply 1, right? Which means that even if I have a normalization constant, at every x I have a constant probability. The probability seems to be constant over the entire space. But this cannot be true, because if the probability the probability is constant everywhere, then the total probability will not be 1. There's no way that you can make the total probability equal to 1. Right? So we say that such wave functions are non-normalizable. These wave functions are actually non-normalizable. They are quite useful, but you cannot really attach a physical system to this wave function. All right. So the position space wave function then becomes a plane wave extending over all space. The probability of finding the particle is just constant independent of x prime. Okay. What does this mean? Right. Let's look at it in this angle. We said that e raised to ikx is the momentum eigenfunction. This is a momentum eigenfunction. Right. This means that if this is the wave function, and if you are measuring, if this is the state, if this is the wave function that represents the state, if I measure the momentum, I'm going to get an exact value h bar k. Right. You can look at it. You can see this by operating minus I h bar d by dx prime on this wave function. Right. This is the momentum operator in the position space. This is the wave function in the position space. So if I act the momentum operator, you see that you will get h bar k multiplied by e raised to ikx. So this is a momentum eigenfunction. We know this because we found this e raised to ikx by looking for the position representation of the momentum eigenket. Alright. Anyway, this is the momentum eigenfunction, which means that this corresponds to a state with a definite value of momentum. This corresponds to a state with a definite value of momentum h bar k. Now this means that if this is the wave function, right, if you are talking about an electron represented by this wave function, it has a definite momentum. It has a definite momentum. There's no uncertainty in momentum, right? But when there's a definite momentum, right, if you know the momentum definitely, if there's a definite momentum, what do we know about the position? We don't know anything about the position. It could be anywhere in the entire space. It could be anywhere in the entire space. So the position becomes completely uncertain. All right. So that's what we mean when we say that the probability of finding the particle is just constant independent of x prime. All right. Momentum is certain. We know with probability 1 that if I measure momentum on this state, I'll get h bar k. Right? Then the position is completely uncertain. It's a plane wave which extends throughout the space, and it could be anywhere in the entire space. Right? And now again, as I said, these are non-normalizable wave functions. We are just using these as examples to understand what's going on in the extreme case. right? Physically we cannot have such wave functions because we cannot use a probability interpretation, right? Later on, when you study scattering, etc., you'll see that we'll still be using these kinds of wave functions, but over there we'll call this as the number density or something like that. All right, instead of probability density, we may call it the number density. All right, but that's for another time. Let's also look at the momentum space wave function when d tends to infinity. All right, we'll see that this behaves like a delta function, which is sharply peaked at h bar k. This can be understood by looking at the momentum space wave function. What happens? So the d dependence appears like this, right? Now what happens when d tends to infinity? When d tends to infinity, the denominator here, right? This entire denominator goes to 0. This entire denominator goes to 0 as d tends to infinity, right? This entire denominator goes to 0, right? Now when this entire denominator goes to 0, this term, right? This term becomes bigger and bigger. Right? So in other words, this term becomes infinity. This term tends to infinity. This term approaches infinity. Right? So as d tends to infinity, this entire term tends to infinity, and exponential of a minus very large number is 0, because we know that e raised to minus infinity is 0. Right? So this goes to 0 when d tends to infinity. That's clear. Right? But there's an exception. What happens when p prime minus h bar k is very small? Right now, the denominator 2h bar square divided by d square could become very small. It could go to 0, right? But p prime minus h bar k also could go to 0, right? Then we have got two small numbers divided. Okay, in other words, this term, right, does not tend to infinity when p prime tends to h bar k. So except for p prime equal to h bar k, except for the point around p prime equal to h bar k, this term goes to infinity and this exponential goes to 0. Okay, but at p prime equal to h bar k, this term still remains small, right? And we have the exponential does not go to 0, right? So we see that this wave function is peaked around p prime equal to h bar k and it's 0 everywhere else. So if we look at the momentum space like that, around h bar k, right, this is the momentum. So around h bar k, I have got a peak and it's 0 everywhere else, right? Where the momentum is deviating from h bar k, this this 2h bar square divided by d square in the denominator will kill the entire value, right? It takes it to 0, right? So we can say that this is peaked at p equal to h bar k. So in the limit d tends to infinity, the momentum space wave function is peaked at h bar k at a definite value of momentum as we expected, right? Now, in the opposite extreme, we can also talk about d tends to 0. Now, you can analyze these conditions as we analyze the momentum wave function here. All right. So, there we'll see that we obtain a position space wave function which is localized like the delta function, but the momentum space wave function is just a constant independent of p prime. Right. So, when d tends to 0, this exponential will go to 1. It will tend to 1, and we simply get a constant. We simply get a constant probability everywhere, right? Actually, not everywhere, for every value of p. Okay, so again, we'll get the momentum space wave function remains a constant independent of p prime, right? Just like we discussed in the case of position space wave function when d tends to infinity. Okay. We have seen that an extremely well localized state is to be regarded as a superposition of momentum eigenstates with all possible values of momenta. Now this reaches back to the uncertainty principle, all right? Because if I take a position eigenstate, or a position eigenfunction, it's not a momentum eigenfunction at the same time. It's not a momentum eigenfunction at the same time. Instead, it's a superposition of all the momentum eigenstates. Right? It has to be regarded as a superposition of all the momentum eigenstates. Right? So if I have a position eigenstate, right? If I have position eigengate, if I make a measurement of position, I'm sure to get x prime. Right? We are talking in an idealized language again, right? But if I take a position eigengate and if I measure momentum, right, I could get any of the eigengate of the momentum operator. So that's why when the position is completely certain, the momentum is completely uncertain. Momentum is completely uncertain. All right. But when we do this, we have to include even those momentum eigenstates whose momenta are comparable to or exceed mc. Right? We have to include also those momentum eigenstates with momentum which exceeds the relativistic barrier, okay? Because the formalism that we have seen here says that the probability amplitude for all momentums are equal. All momenta are equal, right? So if you are talking about a well-localized position state, then the probability amplitude for every momentum value is equal, right? Even if it exceeds mc. Right? But we know that at such high values of momentum, a description based on non-relativistic quantum mechanics is going to break down. Right? We need a relativistic theory. So we are not talking about the constraints of special theory of relativity. All right? We'll have to construct a theory, a new theory, a new quantum theory, which is consistent with the special theory of relativity. That's not what we are talking about here. All right. Now there are successful quantum theories which are consistent with special theory of relativity. An example is the quantum field theory. Okay. Now this is indeed a limitation, right? But even though there's this limitation, the formalism based on the existence of the position eigenkette has a wide domain of applicability, right? So even though this momentum position eigenkette and momentum eigenkette are not exactly physical, right? These do not correspond to physical wave functions. Right? But we can still use this as mathematical tools, and these are very useful. Right? This position eigenkette and momentum eigenkettes are very useful. Okay. As such, they do not correspond to physical wave functions because we'll have non-normalizable wave functions like e raised to ipx. Right? This is a non-normalizable wave function because if I take the modulus square and integrate over the entire space, right? This thing is 1. I'm getting constant for every x, right? So this would be infinite. This would actually be infinite, right? And we cannot normalize it. All right? So these correspond to non-normalizable wave functions, but still we can talk about them. We can use them, all right? We have almost reached the end of the mathematical formalism. In this class, we discussed the Gaussian wave packets. So we looked at this wave function. We looked at the wave function. We calculated the expectation value of position and momenta, the square of position operator, square of momentum operator, etc. And we calculated the product of uncertainties. And we found that the Gaussian wave packet corresponds to the minimum uncertainty wave packet or minimum uncertainty state. Minimum uncertainty. All right. So if the state, if the physical state is given by a Gaussian wave packet, then the product of uncertainties is at a minimum. Right? Now, by looking, and we looked at the corresponding momentum space wave function by taking a Fourier transform of the Gaussian wave packet. Right? We took the Gaussian wave function, found the Fourier transform, and we got the momentum space wave function. Right? Now, by looking at it, we understood that when the position space wave function is spread out, right, it's wide. When it is spread out, then so something like that, if it is spread out, then the momentum space wave function seems to be peaked around a particular value of momentum. All right, and vice versa. When the momentum space wave function is spread out, the position space wave function seems to be more and more peaked. All right, and we related these things to the uncertainty. Right, uncertainty in the measurement, in the simultaneous measurement of position and momentum. All right. With that, I'll conclude this discussion. Thank you.